So, in the previous class, considering the second order PDE with the constant coefficients, we classified them as elliptic or hyperbolic depending on the number of positive eigenvalues of the coefficient matrix A. So, if the coefficient matrix has all the positive eigenvalues or equivalently on all the negative eigenvalues, that just needs change of sign. So, we call it an elliptic equation, and when the coefficient matrix A has n minus 1 positive eigenvalues and 1 negative eigenvalue, or equivalently 1 positive eigenvalue and n minus 1 negative eigenvalues, we call it an hyperbolic equation. So, the other third case now we will discuss in detail, namely n minus 1 positive eigenvalues and 1 zero eigenvalue, equivalently n minus 1 negative eigenvalues and 1 zero eigenvalue. So, there is 1 zero eigenvalue. So, now the matrix is singular, there is a 0 eigenvalue. So, how do we classify this? Again we go back to three dimensional geometry or even 2 dimensional geometry. So, since we have done for the elliptic and hyperbolic 3 dimensional geometry. So, let us go to again 3 dimensional geometry. The level sets of the quadratic, the level sets are nothing but you take this quadratic and equate it to some constant and see what curve or surface it describes in that R3 space. Okay. So, here you consider this quadratic x 1 square plus x 2 square plus or minus x 3. So, x 3 is only of so in fact I should not call it a quadratic because I am adding x 3 there. Okay. So, it is not a quadratic, it is just a function. Okay. So, this is called a paraboloid in 3 dimensions. Okay. So, you just you observe the inclusion of the term x 3. Okay. So, we are adding that. Okay. So, it is not a quadratic, but we are also including a lower order term, and that too in the third variable. See, the quadratic terms are x 1 x 2 and the first degree term is in x 3, not in x 1 or x 2. So, that is also you have to observe, then only you get a paraboloid. For example, if it is x 2 or x 1, again you can absorb that in quadratic and you will not get a paraboloid. So, that inclusion of x 3 term to get a paraboloid is very important, and same thing holds for the PDE. So, we call the equation 1.1 a parabolic equation if p equal to n minus 1 r equal to 1, and so I have highlighted that the reduced equation 1.2 contains a first order derivative term in a specified variable, that is important. So, just like for the paraboloid, the first order the linear term should be in x 3 and not x 1 x 2. So, same thing should happen for the reduced equation, then only we call it parabolic, otherwise the some other classification needs to be done. Okay. So, we will see in some examples later why this additional remark and stress is there on this. So, this is very important. Okay. Then so, in some sense the classification into parabolic class is somewhat difficult, okay. It is not that easy. Okay. So, now we move on to the variable coefficients. So, that is again, so what we can do. Okay. So, again let me just go back there. So, this equation, and now we are considering variable coefficients. So, this a I j, they depend on a variable x in some open set in R n. So, how do we classify now? So, if we want to imitate what we did for the constant coefficient case, what we can do is you freeze the coefficients at a point x 0 in that open set, and then you get a matrix, constant matrix, namely a I j x 0. So, evaluate all a I j's at this point. So, you get some numbers, and so you will get a symmetric matrix, and then we obtain an orthogonal matrix. Again that depends on x 0, and the eigenvalues also depend on x 0. And as we vary x 0 in omega, we get matrix valued functions R x 0, and eigenvalues are also functions of x, and that makes the life complicated. And since we are dealing with partial differential equations, it is not enough that we get these matrix valued functions R x x naught, and the eigenvalue also depending on the variable x, but we also need some smoothness on of the eigenvalues and also on the rotation matrix R x, and these are difficult questions and not dealt with in a typical course on linear algebra. So, in usual linear algebra we never consider matrix functions, okay. And what might happen is the eigenvalues at some x, they may all be positive, but in some other point some of them may be positive and some of them may be negative. So, hence the type changes, the class changes, and it is very difficult to keep track of all those developments. Okay. So, here is a simple example, Trichotomy equation. So, this simple second order equation in two variables y u x x plus u y y equal to 0, and in the region y greater than 0 it is elliptic, and in the region y less than 0 it is hyperbolic. So, we will see when we do classification of the second order equation in two variables, you see y this is elliptic in y positive and hyperbolic in y negative. So, the type changes, and these are more difficult problems to deal with. So, we cannot possibly approach this classification problem of variable equations through this linear algebra. So, that is the message I want to drive at. So, using the usual linear algebra is not possible to classify equations with variable coefficient. Then what we will do? So, we will seek for another strategy, so a different strategy. So, do not look for linear change of variables, but now you look for some functions. So, the change of variable from x variable to y variable. So, y j equal to phi j of x. So, we seek some functions phi j. The first requirement that this phi j should possess is that this non-singular requirement. The non-singular requirement in case of constant coefficients, this R was an orthogonal matrix, and so that is non singular. So, here the non singular requirement means the Jacobian of this transformation, namely determinant of del phi. So, phi j, each phi j is a function of x 1 x 2 x n. Okay. So, we are in n variable situation. So, you consider this matrix of the first order Jacobian matrix of this transformation, namely del phi I by del x j, and then you take the determinant of that. Okay. That should not vanish in omega, okay. That open set omega. So, this is the requirement. Why this requirement? Then the from one variable from x to y, we can go and from y to x. Suppose in the variables y, if it is easy to solve the given equation, then we can come back to the original variables. Okay. So, it is like system of algebraic equations you want to solve. So, usually you bring it to either diagonal form or at least upper diagonal form, so that you can easily solve the given set of algebraic equations. So, a similar strategy we want to adopt for the PDE. Okay. So, now our principal part. So, I am ignoring the lower order terms. Lower order terms are important for the full reduction, but as far as the reduction is concerned, it is only the highest order terms, that is the principal part. So, using this change of variable, you transform this equation into this. So, while doing so, you do get some lower order terms here. I am not considering them. Okay. So, there are lower order terms here, and even this reduction from going from this x variable to y variable also will produce some lower order terms, because the coefficients are variables now, but you club all the first order terms here, first order terms here, and you will get first order, but we are concentrating only on the second order terms. So, what are this a I j tilde? Okay. So, they are easy to compute, some tedious calculation, but simple differentiation. So, you compute them. So, here I am writing. So, a I j tilde is given in terms of a k m and the transformation phi I. So, it is a little complicated, but straightforward to compute. So, you should do that. So, it is just chain rule and implicit differentiation. So, you can do that. Okay. So, now we want this a I j tilde to be 0 for all I not equal to j. Just see that. Okay. So, this if I make all the mixed derivative 0, then this is reduced to a diagonal form, and that is what we want, right, to begin with. Okay. So, at least the first requirement is that if possible we want this a I j tilde for all I not equal to j, and since these are all symmetric, a I j tilde is a j I tilde, there are, just you count them, there are n into n minus 1 by 2 equations. Okay. And these come in the, these are the equations for the phi i's we want to find out. So, there are n into n minus 1 equations. How many unknowns are there? Unknowns are only phi 1, phi 2, phi n. So, there are n unknowns, and we are getting n into n minus 1 by 2 equations. So, a simple observation. So, if n is bigger than 3, then this n minus 1 n into n minus 1 by 2 is strictly bigger than n. So, that means there are more equations and less number of unknowns, and this is an over determined system. So, very difficult to solve. Okay. So, for n bigger than 3, we cannot hope to get such a transformation that transforms the given equation, its principal part, into a diagonal part. Okay. So, that is not possible. So, what about n equal to 3? N equal to 3. So, there are number of unknowns and number of equations are the same. So, there is some hope, but then we also want the diagonal terms, namely a I tilde to be plus or minus 1 or 0, okay, because that is what we did in the constant coefficients, that is the canonical form. Okay. But then these equations are added to that. So, again we are getting an over determined system. So, even for n equal to 3, there is no hope of obtaining such a transformation, and that leaves thus we are left with only one case, namely n equal to 2. So, such a transformation. So, again let me repeat that, finding such a transformation to reduce the principal part of the given differential equation into a diagonal principal part with diagonal terms plus or minus 1 is not possible if n is bigger than or equal to 3, and we are left with only the case of n equal to 2, and now we proceed to do that. So, thus this is the only case we need to consider, and whether there is a possibility of reducing the principal part of this equation. So, this is the principal part, only consisting of only the second order derivatives to a diagonal form. So, somehow in the transformed equation we do not want to see this beta. So, that means this mixed derivative should vanish, and let us see whether that is possible, and we will show that that is always possible. And before proceeding, so the one important simplification we have in case of two variables. See, the quadratic form associated with this principal part is a xi square plus 2 b xi eta plus c eta square. So, let me write it as xi and eta variables, and this, whether it is definite or indefinite, depends only on one quantity, and that is okay, that we seek, and this is the requirement that this transformation is non-singular. So, that determinant I have written it explicitly here, because it is a 2 by 2 determinant. So, just you compute that. So, this should not be 0 in the domain we consider. Okay. So, let me again, so in case of general second order equation in n variables, we wrote this transformation, and now we again write explicitly here. So, just you observe these three quantities. So, here, so there are only three quantities, a tilde, b tilde, c tilde, and they are given in terms of the coordinate functions. So, that we seek, namely phi and psi. Okay. So, you observe these things, because this is what gives us the transformation phi and psi. Okay. This is the important thing. So, I was telling the nature of the quadratic form, whether it is definite or indefinite, depends on only one quantity, namely the discriminant of the quadratic, AC minus B square. So, if AC minus B square is positive, then the quadratic form is positive, and if AC minus B square is negative, then the quadratic form is indefinite, and when AC minus B square is 0, it is semi definite, meaning it is always either greater than or equal to 0 or less than or equal to 0. That all these things just follow from considering the quadratic. Okay. So, that is why it is easier here in two dimensional case, just with two variables. So, what it shows is, so again this computation, this requires some computation algebra here. What it says is, the discriminant has the same sign, whatever the L had. So, AC minus B square, whatever, and the L0 tilde also has. So, if it is definite in xy variables, it is also definite in x tilde, y tilde variables. So, that is an important observation. So, the type does not change under non-singular change of variables. Non-singularity is used here. Okay. So, this is non-zero. So, you are multiplying only by a positive quantity. Okay. So, the type does not change, that is very important. And so, you immediately conclude that the equation 1.3, so name. Okay. So, the second order equation. So, only the first three terms matter. So, we call this elliptic if AC minus B square is positive, hyperbolic if AC minus B square is negative, and parabolic if AC minus B square equal to 0, and the for last one that with reservations. Okay. So, all the time will not be able to call it parabolic, as we see some examples. Okay. So, now we are proceeding to find the transformations. So, that is our goal now. How do we find this phi and psi? Okay. So, the first case we consider is the case AC minus B square is negative, and that should happen not just at one point, but in that open set, that is important. Okay. And in that case, this quadratic equation, when AC minus B square is negative, this quadratic equation has two real and distinct roots, and that is what we learn in high school. Okay. And since A and A, B, C are functions of x and y, this xi1 and xi2 are also functions of x and y. Okay. And this quadratic equation plays an important role. Why that? So, let us just again go back and observe these three quantities A tilde, B tilde, C tilde. So, for example, if phi y is not 0, I can divide by phi y square and then I get A phi x by phi y square, 2 b phi x by phi y plus c, and that is exactly this quadratic. If I replace zeta by phi x by phi y, okay, and phi x and phi y cannot be equal to 0 simultaneously because of the non-singularity condition. Okay. So, you have to pay attention to all these things. So, phi x and phi y cannot be 0 simultaneously, okay, and similarly psi x and psi y cannot be 0. Okay. And similarly, so since psi x and psi y not simultaneously 0, so that psi x by psi y also satisfy that quadratic equation. Okay. So, this zeta we can replace it by phi x by phi y or psi x by psi y as the case may be. Okay. And since xi 1 and xi 2 real and distinct, so we choose that phi x by phi y by the by. So, if for example, what happens if a equal to 0, now you take the zeta square here. Okay. So, that is always possible. If a and c are 0, then we are already in good case. Okay. Let me just mention that, we will see that. If a and c are 0, there is only one mixed derivative, we will see how that can be converted into pure derivatives. Okay. So, that is the easiest case. So, you begin in this case that one of them is not 0. Okay. Simple things, but you have to pay attention to these things. So, as I said now, so we can choose this phi x by phi y equal to zeta 1 and psi x by psi y equal to zeta 2. I am sorry for this, this should be zeta 2. Okay. Zeta 2. So, this phi x and phi and psi satisfy this first order PDE. Okay. So, xi 1 and xi 2 are variable because a, b, c are variables. So, xi 1 and xi 2 are functions of x and y. So, this we obtain phi and psi by solving this first order equations. One thing you should remember here, so though they are first order equation, so you have already learned the method of characteristics to solve first order equation, and here they are linear in fact. This xi 1 and xi 2 are only functions of x and y. So, there is absolutely no problem, but there is no initial line or initial condition. So, in practice when you want to really obtain this phi and psi, some simple functions will do. So, we need not go to the full strength of the method of characteristics. So, even by observation you can write down the some solution. We are not interested in all the solutions, we are interested only in finding some simple solutions. Our only concern is non-singularity, that is important. Okay. So, we have to find phi and psi, so that we get non-singularity, and in this case hyperbolic case it is very easy to verify this phi and psi are non-singular in the sense that phi x psi y and phi y psi x is not 0, because xi 1 and xi 2 are different. Okay. Some simple calculation you can easily verify that. Okay. So, again go back to the expressions a tilde, b tilde, c tilde. So, with our choice of phi x by phi y equal to zeta 1 and psi x by psi y zeta 2, where zeta 1 zeta 2 are solutions of that quadratic equation, you immediately see that a tilde and c tilde vanish. That is the just by looking at the those expressions of a tilde, b tilde, and that zeta 1 zeta 2 are solutions of this quadratic equation. And so, L 0 reduces to, so only the middle term, the mixed derivative. Okay. So, a tilde is 0, c tilde is 0. So, you get only this del square, sorry for that, again del square, del square, del square. Okay. So, just del square, second order derivative, and just this one more step to get rid of that mixed derivative. So, this is a very simple transformation. So, the curves phi equal to constant and psi equal to constant are called characteristic curves of the hyperbolic operator L. This case, so just like the first order equation. So, here there are second order equation. So, there are two characteristic curves, two families of characteristics curves. Okay. And this mixed second order derivative we can convert into pure second order derivatives by this simple transformation. You put zeta equal to x tilde plus y tilde by 2 and eta equal to x tilde minus y tilde by 2, and then this becomes a constant multiple of this operator. I have not written that constant, but that constant you can non-zero constant. So, that you can absorb in the first order terms. Okay. So, in this hyperbolic case we are able to find phi and psi explicitly, and finally getting the equation reduced to a pure second order form. So, this is a typical wave operator. So, del square by del j square minus del square by del eta square. Okay. So, now we go to the next case, namely parabolic case AC minus b square equal to 0. Okay. So, assume a not equal to 0. So, if a equal to 0, what happens? If a equal to 0, then this term is gone. So, b is also 0, and then again there is no second order equation at all. So, if a, b, c are 0, all second order terms are 0. So, we are getting only first order equation. Okay. Because we are considering second order equation, all 3 cannot be 0 simultaneously. Okay. So, either a should not be 0 and c or c should not be 0. So, for definiteness we are assuming a not equal to 0, okay, and similarly c is not equal to 0. And in this case again that quadratic equation, it has only one double real root, namely zeta equal to minus b by a. And in this case the given PDE has only one family of characteristic curves phi equal to constant, and that phi satisfies now the first order equation again. And because AC equal to b square, this is also equivalent to b phi x plus c phi y equal to 0. Okay. So, we could now only find one function, okay, but now we can choose any other suitable function that makes this transformation non singular. And now you observe these two equations and again go back and see this is important again a tilde b tilde. Okay. This time we are not, psi is arbitrary for us for the time being, we have only phi. Okay. And so, choosing the phi we get a tilde 0 and again here if you group it, so you get a phi x plus b phi y psi x and b phi x plus c phi y psi y. So, you plug in these things and observe that in this case a tilde and b tilde are 0, a tilde and b tilde are 0. So, there is only one term remaining. So, this you get del square by. So, for example, here I can simply choose psi x y equal to x just for the argument sake. So, this is we can freely choose. Okay. We will see in some examples. Okay. And that gives important thing is the coefficient of c tilde is not 0 and that gives me del square y, del square divided by del y tilde square. Okay. So, again, so this a caution. So, we have the full equation here, again go back in this case. Yeah, we have the second order equation and in that case A c equal to b square, you reduce this equation in the new variables x tilde and y tilde and the leading term, the second order term is definitely del square by del y tilde square, but unless there is a lower order term in del x del by del x tilde. Okay. So, this is similar to the comment I made on the paraboloid. Okay. So, you have to have a lower order term in the other variable, not y tilde, but x tilde. Okay. Then only you call it parabolic. And here is a classic example when that is not possible for a given differential equation. So, that means the full reduction will not contain this del by del x tilde term, then you call that as weakly hyperbolic. And here is a simple example, you take this operator, okay, second order, and so there is only one here a c minus b square is 0. Okay. So, a is 1, b is 1 and c is 1. So, this a c minus b square is 0. So, there is only one real characteristic, but after the full reduction you will not get this lower order term and this is classified as weakly hyperbolic and not parabolic. So, in this case for two variables we could do full analysis and the analysis just depends on one quantity, namely the discriminant a c minus b square, and we could do reduction in case of hyperbolic and parabolic, and with this caution. Okay. So, either parabolic or weakly hyperbolic we can do that, and now the only case that is left is a c minus b square is greater than 0 and that is bit tricky, that we will take up in the next lecture. Thank you.